Welcome, friends. We are discussing network theory. Presently, we are at module 3. It is all about three-phase AC circuit. Previously, we have discussed two fundamental networks in AC circuit, that is one star connection, second one was the delta connection, and then we have understood the relationship between voltage and currents. That means the relationship between phase voltage and line voltage in case of both star network and delta network, and in terms of current as well, what is the relation between line current and phase current in terms of star network and delta network. We have understood those aspects. We have also seen that power is dissipated in the resistor, and we have derived one formula which was root 3 times line voltage into line current into cos phi, which is power factor. Now in this part of this lecture, we shall mainly focus how to measure power. That means the measurement procedures of power. So we have two fundamental networks again. One is star connected load, another one is delta connected load. So what will be the total power consumption in case of star connected load, and also in case of a delta connected load, how that total power can be measured? Those mechanisms we shall mainly discuss in this present session, or maybe afterwards as well. So we are going into the details. So if you look, that we want to measure power, we have seen power is root 3 times line voltage into line current into power factor, that is the total power. Now if you want to measure the per phase power, then it should be V phase into I phase, that is voltage, phase voltage into phase current and that is multiplied with the power factor, that will be giving you per phase power. So if you want to state this one as terms of phasor diagram, it should be V phase, this phasor, current phasor should be lagging by some angle phi. So the total power consumed is Vi cos phi. So now, since we are going to study the measurement procedures of the power, then first we need to know who measures power. Measures power. The answer is quite obviously wattmeter. Answer is quite obviously wattmeter. Now, and wattmeter, if you consider this figure 6, this diagram The first diagram represents the symbol of wattmeter or different terminals, you can say, of the wattmeter. Now, in order to understand how wattmeter measures power, this is very important to understand. Now, primarily, wattmeter has got 4 terminals. Primarily, wattmeter has got 4 terminals. We have first M, this is number 1 terminal. Then we have got L, second terminal. Then we have got our third terminal C, and then we have got fourth terminal V. There are 4 terminals of a wattmeter. Now the coils connected between terminal M and L is called CC, or it's called current coil. Current coil. On the other hand, the coil connected between terminal C and V, it's called potential coil or pressure coil. It's called potential coil. So since the wattmeter measures power, so power has got 2 fundamental components, one is voltage and one is current. So the current is basically measured by current coil of the wattmeter, and the voltage is measured using the potential coil of the wattmeter. So let me recap again. Wattmeter has got 4 terminals. First one is M, second one is L, third one is C, and fourth one is V. The coil connected between M terminal and L terminal is called current coil, and in short, simply it is called CC. And the coil connected between C terminal and V terminal, it's called PC or pressure coil or potential coil. Since wattmeter measures power and power is equal to, fundamentally it is equal to voltage into current, so the voltage is measured using potential coil and current is measured using current coil. So as a result, if the wattmeters are to be connected or are to be connected to any circuit, then remember one thing, that this current coil must be connected in series with the rest of the networks. Because it measures current, the current will be flowing through the current coil, and this potential coil you have to connect with parallel to each other. The pressure coil has to be connected parallel to either of the supply or to the load to measure the voltage of the supply. So because potential coil is measures voltage, so current coil should be connected in series. Current coil should be connected with the series with the maybe ammeter. This is an ammeter. And pressure coil or potential coil must be connected parallel to the supply or maybe load in order to measure the voltage, of the supply or to the load. So figure 6, the right hand diagram it represents the circuit diagram of wattmeter. So this is the single phase AC supply. So from there we have a regulated AC supply, is called variac. So from that variac, input terminal of that variac, this is the input terminal of the variac. That terminal is connected to M terminal of the wattmeter. Then From the L terminal, a ammeter is connected in series. Then from that ammeter, we have connected a load in series, and this load is coming to the return path to the source in this fashion. So this completes the circuit. Now we have left this potential coil. So first we need to short these M and C terminals. Then these V terminals has to be connected to the supply neutral terminals. Okay. So in this way, if you do like, first M and C should be shorted, and then this V terminal of the wattmeter should be connected to the neutral terminal or the return terminal of the supply. In this way, this potential coil, this entirely potential coil is connected to the parallel to the supply. You see, in this way, this entire potential coil is connected to the parallelly to the supply terminals. So this is the connection diagram of wattmeter. Now wattmeter measures powers, that's all right, but what is power? What is power? Power is basically V into I cos phi. And what is this phi? Phi is the angle between voltage and current. Angle between voltage and current. So wattmeter measures voltage and current, that's okay, but what is this phi? So phi is basically nothing but angle between voltage and current that wattmeter measures. Let me repeat that statement. Power is equal to voltage into current into power factor, where phi is the angle between voltage and current, that is okay. Voltage is measured by the potential coil, current is measured by current coil. However, what is phi? So phi is this angle between voltage and current. That voltage must be measured by that wattmeter, and that current must be measured by that wattmeter itself. So basically the phi is the angle between voltage and current, that to be measured by the wattmeter itself. So later on we shall show you that, we shall see shortly that for a same circuit, if we connect wattmeter differently, then power readings will be different. That is a very strange thing. For a same circuit, if you connect wattmeter differently, then your wattmeter reading would be different for each case. So we shall shortly demonstrate that example. So it will be totally dependent on how you are connecting your wattmeter connection, and depending on the connection, this phi will change. That is the angle between voltage and current, because at each time the wattmeter measures different voltages. Naturally, when it measures different voltages, the angle changes, angle keeps changing. So that is why each time wattmeter measures different power. So that is very important to understand that wattmeter reading is totally depending on the wattmeter connection, how current coils and pressure coils are connected. If you change them, your reading of the wattmeter will totally change. So we shall shortly demonstrate that fact. Now let me quickly revisit before going to the star connected load, how to measure the power of a star connected load using the wattmeters. So before that, we want to revisit the previous day's work, or previous classes work rather. We have understood that So we have understood that yesterday, or the last from the last lecture. So this is actually your first phasor is your first phasor is VR. Your second phasor will be Vy. Second phasor will be Vy, and your third phasor will be Vb. Third phasor will be Vb displaced by an 120 degree. So now if we want to measure Vry, then you should produce this Vy in the negative direction. You should produce this Vy in the negative direction. So this will be Vy. So with that, if you add vectorially, so this will be your actually Vry. So this is actually your this phasor is your Vry. We have seen this. So similarly, if we want to measure Vyb, then your V phasor has to be produced in the negative direction, like this. So this will be your minus Vb. So now if you add them by phasor, so it will be Vyb. It will be Vyb. And similarly, lastly, if we want to measure Vbr, then your R phasor has to be produced in the negative direction. This should be minus Vr. So if you add them vectorially, then the answer should be like it is Vbr. So these all are this Vry, this Vyb, and this Vbr, all are line voltages. And this Vr, Vy, and Vb, they are all called phase voltages. So this much we have understood from the previous lecture. And we have also understood one thing, that if you consider a load, that is, this is the load current, maybe this is the IR. So this angle is the load power factor angle. So this should be phi. So similarly, this should be also IY, and this should be also IB. So all they are lagging, all the respective phase currents lagging by an angle of phi, that is called lagging power factor angle for a balanced load. Now you are going now to understand the wattmeter connection. To understand the wattmeter connection, has got two coils, current coils, and second one is pressure coil. Current coil measures current and pressure coil measures voltage. Now wattmeter measures the angle between this measured voltage and current. Wattmeter measures the angle between measured voltage and current. Measured voltage and current. That is the reason, depending on the connection of the wattmeter, the power wattmeter readings are changed. So we have fundamentally understood this diagram. Now from this diagram, from this phasor diagram, we can pick any two phasors that a wattmeter measures. So let us check. So let us say this is the connection diagram to measure the total power by three-phase load. Now this load is star connected. So we require two wattmeters. We require two wattmeters for that. Now see, this is the first wattmeter, wattmeter 1, W1, and this is the second wattmeter, W2. Now wattmeter 1 has got current coil, wattmeter 2 has got also a current coil. Similarly, both the wattmeters W1, W2 has got potential coil. So we have connected in this fashion. Now how we connected? We have connected current coil in series with the R phase. You see, this is R phase actually. So we have connected R phase in series with the current coil like this, and we have connected that current coil straight to the load. So this will be connected in series. So this current coil, the wattmeter 1 has got wattmeter 1 current coil is measuring actually I into IR, that is the phase current of IR. So current coil of wattmeter 1 measures phase current of IR. Similarly, if you consider wattmeter 2, this is Y phase, so current coil of wattmeter 2 is connected in series with Y phase, just like this. So this is Y phase. So it measures phase current of Y phase only. So wattmeter 2, it has got a current coil, so it measures nothing but phase current of IY. Now if you are considering now the pressure coil of the wattmeter 1, the pressure coil of the wattmeter 1 is connected, you see, one terminal, that is common terminal, is connected to M, and the voltage terminal or V terminal is connected to this term or this point, which actually the B phase, because this is B phase. So actually in this way we can understand that the pressure coil or potential coil of the wattmeter 1 is connected parallelly across R and B phase, because one terminal is connected to the R phase and another terminal is connected to the B phase. So pressure coil of the wattmeter 1 is connected parallelly to the R and B phase. So basically pressure coil of the wattmeter 1 or potential coil of the wattmeter 1, potential coil of the wattmeter 1 measures the voltage which is nothing but VRB, which is nothing but VRB. So pressure coil of wattmeter 1 is measures nothing but the voltage VRB because it is connected across R and B supply. Now similarly, if you consider the wattmeter 2, you see the pressure coil of the wattmeter 2, the C terminal is connected to Y phase, C terminal is connected to the Y phase, and V terminal is connected to again B phase. So the pressure coil of the wattmeter 2 is connected parallelly across Y and B, parallelly across Y and B. So it is measure a voltage which is nothing but VYB. So wattmeter 2, that is pressure coil, is measuring the voltage which is equal to VYB. So from this connection diagram we have understood that current coil is connected in series with the R phase. For wattmeter 1, current coil is connected in series with the R phase. That is why it is measuring IR current. And pressure coil of the wattmeter 1 is connected parallelly with the R and B phase. That is why it is measuring voltage of VRB. And similarly, for considering wattmeter 2, if that is the current coil is connected in series with Y phase, that is why it measures current IY, and the pressure coil or potential coil is connected parallelly to the Y and B phase, that is why it measures voltage VYB. Now from the phasor diagram, which is drawn just to make you understand that you see the current coil, current, that is wattmeter 1, current coil carries current of IR. So this is the IR. And pressure coil measures voltage VRB. So the pressure coil measures voltage VRB, right? This is VRB. So where is VRB here? VRB is this. Actually, this is not VRB, this is VBR. So if you can produce it in the negative direction, it becomes VRB. It becomes VRB. So if you produce in the negative direction like this, roughly it will become VRB. So this is VBR. So if you produce them in the negative direction, it will become VRB. So the angle between VR phasor and VRB is nothing but it is 30 degree. So the wattmeter measures, so this angle between VRB and IR is nothing but 30 minus phi. It is nothing but 30 minus phi. So in this way we can say that, in this way we can say that the angle between VRB and IR is nothing but 30 minus phi, just demonstrated here. So this is VRB, just shown now. This is IR. So this angle is 30 degree. So the angle between this is only 30 minus phi. So now let us coming to the Let us coming to now W2. Now W2 measure IY and VYB, these two, IY and VYB. Let us figure out IY and VYB. So here it is IY, this is IY, and where is VYB? VYB is this. So actually this angle is 30 degree. Actually this angle is 30 degree. So the angle between VYB and IY is basically, so wattmeter 2 measures IY through current coil and it measures VYB through pressure coil. So angle between them is nothing but this is 30, this is phi. So the angle between them is 30 plus phi. 30 plus phi. So wattmeter 1 readings, if it gives the power of P1, then P1 must equal to VRB into IR, and the angle between them is 30 minus phi. So it should be cos 30 minus phi. And similarly, if wattmeter 2 gives a power rating of P2 or reading of P2, so it will giving you VYB that multiplied by IY into cos 30 plus phi. So in this way, if you change your wattmeter connection, this angle will change. Just we have seen that we have connected these two wattmeters differently, so it will measure different voltage and current. That is why the respective angles between voltage and current change. It is for wattmeter 1 it is actually 30 minus phi, and for wattmeter 2 it will be 30 plus phi. So we have understood that the reading of the wattmeter 1, is VRB IR into cos 30 minus phi. Now VRB is line voltage, so we have mentioned VL. IR is also, it is phase voltage, but in case of a star connection, line voltage becomes line current becomes phase current. So IL is written, and the angle between them is cos 30 minus phi. So therefore P1 is equal to line voltage in terms of phase voltage, so it will be √3 times V phase. So IL becomes I phase, so it will be cos 30 minus phi. So altogether we have a relation P1 is equal to √3 V phase into I phase cos 30 minus phi. Similarly, for wattmeter 2 we will get the similar sort of equation, but this time we will have √3 V phase I phase. Now angle between them, just we have understood, it is 30 plus phi. So if you add them P1 plus P2, which is actually the total power consumed by the entire circuit, so it will be √3 V into I. Let us replace V phase by V and I phase by I. Then we have a relation cos 30 minus phi plus cos 30 plus phi. Plus cos 30 plus phi. That becomes the total power. So now if you break, cos 30 minus phi equal to cos 30 cos phi plus sin 30 sin phi. and cos 30 plus phi becomes cos 30 cos phi minus sin 30 sin phi. So if you solve this equation, it will become root 3 v phase I phase or root 3 vi. Now this sin term sin 30 sin phi will get cancelled. So it will become 2 cos 30 cos phi, 2 cos 30 cos phi. So if you solve this, it will become total power of is 3 vi cos phi, that is 3 v phase into I phase cos phi. So from this expression, that is total power, which is coming 3 v phase I phase cos phi, which is nothing but the total power consumed in the three-phase circuit, because for each phase power consumption is v phase I phase cos phi, v phase I phase cos phi for each phase. So there are three phases, so the total power consumption will be 3 v phase or 3 vi cos phi simply. So we can understand that for a three-phase circuit like this, we have a load, three-phase load, star connected load. Now if we install the 2 wattmeters to measure the power, then that 2 wattmeters will be sufficient to measure the entire power. That means we do not require 3 wattmeters to measure the total power. That means one perception may be like that, there are 3 phases, so we require 3 wattmeters to calculate or to measure total power. So no, we have proved that if we have 3-phase system, so total power consumed by the 3-phase system can be measured by two number of wattmeters. 2 wattmeters will be sufficient to measure the power consumed by 3-phase circuit. So just here that each phase, that means this is the power consumption in our phase, that is VR IR cos phi, which is V phase I phase cos phi. So this is consumed in Y phase, Vy Iy cos phi. So again another V phase I phase cos phi comes. And finally, this is the power consumption in B phase. So another V phase. So altogether we have 3 Vi cos phi consumed in the our 3-phase circuit. So wattmeter 1, as already mentioned, wattmeter 1 will read IR by its current coil and VRB by its pressure coil. Angle between them is 30 minus phi. On the other hand, if we carry the similar study in case of wattmeter 2, then it will read IY by its current coil, it will read VYB by its pressure coil, and the angle between them is 30 plus phi, as can be understood from this diagram. So this is VYB and this is IY, so this angle is 30. So the total angle becomes angle between VYB and IY, this total angle becomes 30 plus phi. So if you substitute that, wattmeter 1 will read this much, wattmeter 2 will read this much. So the total power becomes, we have solved and we have proved that total power becomes 3 V phase I phase cos phi, which is exactly matching with this result. That is the for an actual case what should be the power consumed by a 3-phase circuit. So this is where we can conclude that 2 wattmeters are essential, or 2 wattmeters are required to measure the power consumed of a 3-phase circuit. So that is a very important statement. Now, if we carry out the derivation further, then we have a calculation like P1 minus P2. So then P1 minus P2 will be given by this formula. So again, this root 3 V phase I phase term comes outside, and if we break, cos 30 minus phi becomes cos 30 cos phi plus sin 30 sin phi, and then we have carried out cos 30 plus phi, so then cos 30 cos phi plus sin 30 sin phi. So if you solve this, then this cosine terms will be going out, will cancel each other, and we have P1 minus P2 will be equal to 2 sin 30 sin phi root 3 V phase I phase. So if you solve, you will get root 3 V phase into I phase sin phi, and we have previously we have found P1 plus P2 is equal to root 3, not root 3, 3 actually, 3 V phase into I phase cos phi. So now if you divide this, okay, so in the numerator or in the one side we have numerator P1 minus P2, and in the denominator we have P1 plus P2, then this V phase I phase will be cancelled out. So from these two equations we shall have P1 minus P2 by P1 plus P2, which is equal to root 3 by 3 into tan phi. And from there we have got the phi is equal to, or load power factor angle, given by this formula, which is very, very important. That is, the load power factor angle is given by the formula, or you can, some other way we can say that load power factor angle is also dependent on the two wattmeter readings. How? We can say that if for a unity power factor load, we have phi is equal to 0, because for a unity power factor load, voltage and current are always parallel to each other, no phase displacement. So we have phi is equal to 0. So from that relation we can say that if phi is equal to 0, then P1 must be equal to P2. So both the readings are equal. This is number one observation. Secondly, we have, if we have phi is equal to 60 degree, then one of the parameters will give you 0 reading. One of the wattmeters will show you 0 reading. From this expression, if phi is equal to 60, then one of the wattmeters, then you see this term will go out, so then P1 must be equal to P2. Sorry, if you substitute phi is equal to, so tan 60 will become root 3, so that root 3 becomes cancelled, so P1 minus P2, that will becomes P1 plus P2. So from there we can clearly say that P2 must be equal to 0. So one of the wattmeters must be, reading of the one of the wattmeters must be 0. Furthermore, if we have phi is equal to 90 degree, that means if you have a purely resistive or inductive circuit, sorry, not resistive, we have either purely inductive circuit or a purely capacitive circuit. So for that case, the two readings are equal but opposite to each other. So reading of the one of the wattmeter is negative. That is very important. Reading of the one of the wattmeter is negative. To rectify that, either terminals of the current coil or pressure coil has to be interchanged. So that is also possible when you have a highly inductive or highly capacitive circuit, then one of the wattmeter readings may be negative, just shown in this equation. So in order to rectify that, either current coils or the pressure coils are to be interchanged. So we have understood that pressure coil and current coil measures voltage and current flowing through the wattmeter respectively, and P is equal to VI cos phi. This phi actually measures the angle between measured voltage and measured current by the pressure coil and the current coil respectively by the wattmeter. Because you can connect wattmeter differently, so it is quite obvious that for different connection, this phase angle between different voltage and different currents will change. So naturally, for a same circuit, if you connect your wattmeter differently, your wattmeter reading will change. So just we have studied the power measurement of a three-phase star load using 2 wattmeter method. One of the wattmeters showing the reading V into I cos 30 minus phi. Here the angle between voltage and current is 30 minus phi. On the other hand, for the second wattmeter, it is the angle measured between voltage and current. It's 30 plus phi. So in this way, we have shown that if we connect 2 wattmeters for a three-phase circuit, those 2 wattmeters will be sufficient to measure the total power of a three-phase circuit. And also we have derived a load power factor that is dependent on the wattmeter readings. There we have seen for phi is equal to 0, that means for a resistive load, 2 wattmeter readings are equal. Also we have seen for phi is equal to 60 degree, one of the wattmeters are showing 0 reading. And lastly, we have seen if the circuit or if the load is highly inductive or capacitive in nature, then one of the wattmeters may show negative reading. That means its indicator will be striking in the negative direction. So in order to get the accurate reading, either current coils or the pressure coils terminals has to be interchanged. So in the next session, we shall demonstrate few problems where we can clearly understand that how wattmeter readings can be changed by changing its terminal, provided that wattmeter is connected to a same circuit. But when you connecting its terminal differently, it will give you different readings. So I am ending here this part. So let us continue this topic in the next session. Thank you.